Alright class, I just got a request to look at this problem 3.4.17. It's your problem number 10 in your actual homework. So a lot of this is just visual, just looking at this, but it's also just your understanding the relationship between position, velocity, acceleration. So I'm going to blow this up and move it over to the, oh, I can't move it other side. Well, I will pop it up as needed when we're looking at it. It wants to know how fast was the rocket climbing when the engine stopped. So if you read the, when you read this, it talks about it burns a few seconds accelerating. It coasts after there, so that's where the engine has stopped, is where it's coasting. So that's going to be right here. It's accelerating it upward, and then it's the engine stopped, and it's still rising because velocity is still positive. So this is not. This is velocity. This is not the rocket. The rocket is not rising and now the rocket's falling. The rocket is rising as long as velocity is positive. Let me grab a line here. There's the zero value. So anytime we're above here, it's positive. That means it's increasing its distance in feet above the earth. So it's rising, the engine stops, it's still rising, it's still rising, it's still rising, and now its velocity is negative, so it's falling. Okay, so you have to understand that zero line is really important here because that is the difference between upward motion, positive velocity, and downward motion here, negative velocity. So do make sure you understand that big important component of this. All right, how fast was the rocket climbing when it stopped? So if we blow that up and look at it, it looks like I can't really even see that in that window. So this is 150, 160, 70, 80, 90. So it looks like it was 190 feet per second. And then it wants to know how many seconds did the engine burn. The engine again is burning as long as we're on this like parabolic arc, this part of it. So if we look at our values, what number is this axis right here? That is 4 seconds. And then it wants to know when did the rocket reach its highest point. Alright, these things always reach their highest point when velocity is 0. Right, when we have that change in velocity from rising to falling. So what we're being asked to do here is again to estimate what is the coordinates of that intercept right there. So if I again estimate where are we right here, let me draw it in again with those values along the t-axis in there. Where are we when we hit this intercept right here? So it looks like about right at about 10 seconds is what I'm estimating is that value of that 0. So at 10 seconds we reach our max. Okay. All right. What was the velocity? What was the rocket's velocity when it reached its highest point? It's 0. That's what we just said. That's why we have to look for that 0 value. What's the x coordinate or t coordinate when we reach 0 the second time? So it's 0 to start. When does it reach 0 velocity again? All right. When did the parachute pop out? The parachute is we're descending. So we've descended for a little while. Now the velocity is negative. Again, let me draw that back in there. We've descended for a little while once we've achieved that value right there. So once again, this is 10, this is 12. So there's 1, 2, 3, 4, 5 points between those. That's a gap of 2. So 2 divided by 5 is 2/5 or 0.4. So 2/5, 4/5, 3/5. So you can think of it as 10.4, 10.8, 11.2 seconds is where we hit that sharp change. We're dropping fast, and this slows our descent. Now we start abruptly slowing down our descent as we fall. All right, we're still falling though because we're still negative. We're still below. It's just slowed the rate at which we're falling. to a safer speed to fall at. All right, so that was again 10.4, 10.8, 11.2 seconds. So you have to pay attention to the little tick marks and what each tick mark would represent. How fast was it falling when the parachute popped open? So now we're just looking along the axis this way. That is that tick mark. So that's 1, 2, 3, 4, 5 is at negative 50. So that's at negative 40. All right, it's falling, so we don't have to put the negative. So it's asking about it's falling, so we can just leave it as positive 40. How long did it fall before the parachute opened? Well, that's the difference between this 11.2 when the parachute popped out and the time it took to reach its highest point. That was the velocity 0. That was the sign change as well, to go from rising to falling. So now we're falling, so it fell from 10 seconds to 11.2 seconds. So that's 1.2 seconds before the parachute opened. All right, and then when was the rocket's acceleration the greatest? So acceleration is the derivative of velocity. So again, what we're being asked to do here, let me go back to this picture, is where would the tangent lines of this be the steepest? So imagine tangent lines being put on here. If I put a tangent line, on there right there, there's a tangent line right there. Now this is obviously linear, so its tangent line is that line, and then a tangent line right there at that change. That's the steepest tangent line I'm going to see on here anywhere, is that one right there that corresponds to that highest point. Alright, so that was when t was equal to 4. So the greatest acceleration happened 4 seconds after launch, right as the rockets cut off. Constant acceleration, again, the derivative of velocity. The derivative of this thing is acceleration. So the derivative, the tangent line slopes are changing again all through that parabolic looking start to this. So we're getting different tangent lines, right, all through there. We're getting different tangent lines slopes all through here. So it's changing there, but it's constant here. The tangent line is this line. So the tangent line slope is always the same from when the linear part starts to the linear part ends. So from 4 to our parachute opening there at the 11.2. And what was the acceleration then? Well, the acceleration is the derivative of this. So the acceleration would be the slope of that line. So what we'd have to do is estimate the velocity at those points and then find the slope. So there's part of it is the 190 at 4 seconds. So that's 4 190 is that point. And then down here we said that was 11.2 and negative 40. So these are our 2 points, and we're just being asked to find what's the slope between these 2 points. So if you just subtract your change in y's, so 190 minus negative 40 is 190 plus 40. That's 230 is my change in y's. All right, and then my change in x is the 11.2 minus the 4, which is 7.2, and then if I divide 230 divided by 7.2 is 31.94. All right, and that's downhill, that's negative. That should be, sorry, one of these should be negative. I did 11.2, so I did this minus this, so that should be a negative 230. So that's a negative 31.94 repeating is my velocity. I'm sorry, it's my acceleration. It's the slope right there, and the units of slope are the y units per the x units. So feet per second, which is feet per second squared. So it's just the change in y over the change in x from the left end of the linear part of the graph to the right end of the linear part of the graph. and they want it as the nearest integer, so that would be negative 32. All right, so instead of 31.94 repeating, we just round it to negative 32. All right, and then, that should look familiar to you. Okay, remember what we're doing here is the rocket takes off. It's got engines that are thrusting it upwards, fighting gravity, and then the engine, the burn kicks out, and it's not pushing anything up anymore. So it's lost its acceleration, and now the only acceleration is acceleration due to gravity, and that's why we're seeing that negative 32 feet per second constant. All right, until the parachute kicks in, because the only thing that's acting on that object right now, we're assuming, is just gravity, and that's the acceleration due to gravity that we're seeing right there.